Hi, this is Mrs. LaBarbara. This is Physics Chapter 6, Momentum and its Conservation Video 3. Today's topic is the law of momentum conservation. The objectives are to understand the law of conservation of momentum is the result of Newton's third law, to be able to apply equations to solve collision problems, and select sketch vectors that shows the magnitude and direction of a momentum and or impulse. The law of action-reaction revisited. In a collision between two objects, both objects experience forces that are equal in magnitude and opposite in direction in accord with Newton's third law. So Newton's third law says for every action there's equal and opposite reaction, but action and reaction are acting on different objects. Let's consider a car and a truck. When they collide, the force on the car and the force on the truck are the same because that's the action and the reaction force. However, we see the car has bigger acceleration than the truck. That is because of second law. Acceleration is inversely related to mass. While the forces are the same in magnitude and opposite in the direction, the acceleration of the objects are not necessarily equal in magnitude. According to the second law, the bigger the mass, the smaller the acceleration, and the smaller mass, the bigger the acceleration. So when two objects collide, for every action there is equal and opposite reaction. Also, the collision time must be the same. That means the impulse has to be the same. F1 times t1 must be equal to negative F2 times t2. The impulse are equal in the magnitude and opposite in direction. So we have learned impulse momentum theorem. Impulse equals to changing momentum. So that means changing momentum for object 1 must be equals to changing momentum in object 2. In this equation, delta V1 is the velocity change of object 1 during collision. Change means final minus initial. V1 prime is the velocity of object 1 after collision, and V1 is the velocity of object 1 before collision. So delta V1 equals V1 prime minus V1. Same thing goes for delta V2. Delta V2 equals V2 prime minus V2. So we change delta V1 equals V1 prime minus V1. Delta V2 equals V2 prime minus V2. We rearrange this equation. So this is the equation we have. This is the total momentum before the collision. That means momentum of object 1 plus momentum of object 2 before collision equals to the momentum of object 1 and the momentum of object 2 added together after collision. Simply put, P before equals to P after. That means this equation means total momentum of the system remains constant. This is the direct result of Newton's third law, F1 equals to negative F2. If the momentum lost by one object is gained by another object, then the total amount is the same. So this is the equation says M1 delta 1 equals negative M2 delta 2. That means what the lost by one equals the gained by the other. Momentum conservation principle. So the law of conservation momentum states that for a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. That is, the momentum lost by object 1 is the same as the momentum gained by object 2. Conserved means constant or not changing. Take a look at this, another animation for collision, the truck and the car. Total momentum before 60,000 and 0, after is 30,000, 30,000. Again, 0 and 60,000, after 30,000, 30,000. So during this process, looks like the truck has lost 30,000 momentum. And where did it go? It went to the car. The car had gained 30,000. So after is the same as before, total. So this conservation momentum only occurs in isolated system. So what is an isolated system? Let's see, what is a system? A system is a collection of two or more objects. An isolated system is a system which is free from the influence of net external force, which alters the momentum of the system. So it's just the system in between. Here is an example of isolated system. Take a look at the forces. There's gravity, normal force on the object on the left, and the same normal force and gravity on the right side. Another force is the force in between the two objects. This normal force and gravity can cancel. Why can they cancel? Because they are acting on the same object. This normal force and gravity can cancel because they are acting on the same object. But F applied and F applied, these two cannot cancel because they are acting on the two different objects. These are action-reaction forces. So this is an isolated system. So in reality, however, momentum can be approximate to be conserved for every situation due to friction, because in everyday situation, there is always friction, there is always air resistance. But the friction is very small compared to the impact force when during collision. That's why friction can be ignored. Therefore, momentum is approximately conserved. Let's take a look at this example. We're going to check these collision systems to see if they are isolated or not. If it's not isolated, indicate what external force is. So here's a two car collide on a gravel road on which frictional force are large. So what is the system? The system contains these two cars. Is the system isolated? No, because the friction force acting on the two cars are large. So the answer is no. What is the external force? The external force is the friction force. Now let's take a look at this another system. Hans Fu is holding two eggs and tries to crack them against one another. Now, what is the system? The system is two eggs. Is this an isolated system? The answer is no. Why not? Because Hans is applying forces on the two eggs. Applied force on two eggs. Now, how about the next one? Two air track gliders collide on a friction-free air track. So what is the system? System is two gliders. And these two gliders are isolated system because there is no friction. The other forces are gravity and normal force that balance out each other or cancel out each other. So this is an isolated system for situation 3. Now let's talk about a vector diagram for conservation momentum. Consider a fullback plunges across a goal line collide in mid-air with a linebacker in a football game. So mid-air means there's no friction, right? The linebacker and fullback holds each other and travels together after the collision. So before the collision, the fullback possesses a momentum of 100 kilograms times meter per second east, and linebacker possesses a momentum of 120 kilograms times meter per second west. So the total momentum before the collision is you simply add this together. If east is positive, west has to be negative. So the answer is 20 kilograms times meter per second west. So that's the total momentum before the collision. Therefore, the total momentum after collision must be the same because momentum is conserved. This is an isolated system because they are colliding in the mid-air and friction can be ignored. To show a vector diagram, this is what you're going to show. A fullback is to the right because that's the east. P equals 100 kilograms times meter per second. The linebacker is to the left. That's 120 kilograms times meter per second. This is before the diagram, before collision. After collision, the two add together, so you have a net of 20 kilograms times meter per second going to the west. This is combined unit. Now we can use equations to solve problems. So this is the equation, P before equals to P after. Momentum before equals to momentum after. Before, you have to add the two together. After, you also have to add the two together. V1 is velocity of M1. Here are what each symbol represent. Mass of object 1, V1 velocity before collision, V1 prime velocity after collision. Similarly for V2, and v2 prime and m2. Remember, velocity is a vector quantity, so direction is extremely important. Let's take a look at this example. A 2-kilogram ball travels north at 5 meters per second, collide head-on with 1-kilogram ball travels south. So if north is positive, south has to be negative. At 8 meters per second, what is the magnitude of total momentum after collision? Well, we already know P before equals to P after. If we want to know P after, we just have to know P before. So what is P before? M1 V1 plus M2 times V2. That is P before, and that equals to P after. So let's write down what we know. M1 V1, M2 V2, V1, north is positive, south has to be negative. What is P after? Simply plug all the numbers in, and that's what you'll have for P after. Make sure, again, momentum is a vector quantity. It has magnitude and a direction. Example 2, a 3,000-kilogram truck moving with a velocity of 10 meters per second hit a 1,000-kilogram parked car. The impact caused the 1,000-kilogram car to be set in motion at 50 meters per second. Assuming that momentum is conserved during collision, determine the velocity of the truck immediately after the collision. So this is collision problem. We said assume the momentum is conserved, so we have P before equals to P after. What does that mean? M1 V1 plus M2 V2 equals to M1 V1 prime plus M2 V2 prime. By the way, only this equation is in the reference table. So it would be helpful if you write this in your reference table, but you do need to remember it when you take Regents exam. This is what M1 V1 plus M2 V2 equals to M1 V1 prime plus M2 V2 prime is what P before equals to P after mean. Write down what you know, substitute your numbers into this equation with the units, then answer with the units. So V equals to 5 meters per second. That is truck's velocity right after the collision. That's it for today. Thanks for watching. See you next time.